share my screen. Okay, so remember what we were talking about. So I introduced partitions and the pictorial representation of them as Young diagrams. Okay, so then I introduced the Q analogues of integers and just told you that the Q binomial coefficient, the analog of the binomial coefficient, also called the Gaussian polynomial, is a polynomial, and I will leave this as an exercise to prove that the weighted Q sum of partitions inside an m by n rectangle is the Q binomial coefficient. So I'll give an example shortly. Okay, so right, so let me continue on this theme to build on what we had done earlier. So instead of so instead of counting all partitions inside an m by n box, I can do something a little more special. I can ask for partition enumeration with symmetries. So here's a question. So find. Oh, okay. Or maybe before I define the question, before I state the question, let me define the notion of conjugate. So for the partition lambda, conjugate of lambda denoted lambda prime is the partition whose Young diagram is the transpose of lambda. Okay, so I'll need this figure later. Let me move it down. Okay, then I need it. I'll pull it back up. So, okay, so this is the definition, and so maybe I should give an example. So the conjugate of, let's say, 4 to 1 is so there are 4 to 1 like that. So 3 to 1 1. Okay, so how do I see this? Maybe I'll show it on Sage. So here is the. Okay, so what I'll do is partition. So I'll do 4 to 1. So there's one neat command that I did not show you. That's PP. So this stands for pretty print. it's an ASCII print. So you can see that this prints 4 to 1. And now I can do p dot conjugate. And that will give me 3211 as promised, and I can pretty print that as well, and you can see what's going to happen. So I take the diagonal here and I reflect the partition of the diagonal, and I get this partition. And if you read it out, okay, so maybe I should have done. So oh, okay, that didn't. Oh, okay. So the conjugate is that, and it's so the underscore calls the last output. So this dot pp is the pretty print of the partition 3211. As you can see, you count columns instead of rows. That's another way of saying it. Okay, so then the question that I want to ask is, now I can state it easier. So what is the sum of lambda inside n to the m? So, oh sorry, this time I want m to the n. So in m by m square such that lambda equals lambda conjugate of q to the size of lambda. What is this equal to? So this again I'll give you as a homework problem. Okay, so these are symmetric partitions. So let me show you how to do this in Sage. So okay, so Sage has a nice class called Partitions in Box. So here it is. So let me call it P. So this is integer partitions which fit inside a 4x4 box, and if I list P, I'll get a huge list. So let me not do that. Now let me see. So P for P in P, if P is equal to its conjugate. So you see the empty partition is okay. Maybe I can pretty print all of them. That looks helpful. Okay. So 2, 1 is its own conjugate, 2, 2 is its own conjugate. So all of these are partitions which fit inside. So what I can do, for example, is p dot size. I'll do it in this way. P comma p dot size. So this lists both the partition along with its size, and I can do something which is related to the homework, which is to sum. This will give me an error, but it's good to see these errors. So the point is that Q is not defined. So as I told you last time, that except for X, which it takes as a variable, Sage wants you to define everything. So you say Q, you declare Q to be a variable. And now if I sum, I'll get this sum. So note that everything does not have coefficient 1. So there are two things of size 8, 4331 and 4422. No, sorry, that's all. 4211 and 332. Both are size 8. It's okay. Okay, so there seems to be some question in the chat. Okay. So that's clear. So this is related to this exercise. The other thing I can do, and unfortunately, so this also illustrates one of the drawbacks of Sage, is to look at partitions. So, okay, so maybe I'll draw it as a rectangle. So if I draw, so let me draw a rectangle, and let me draw some lines. So this is lambda inside, let's say, M. So which way did I have it? So M0. So this is M. Yeah. So this is M comma 0, and this is 0 comma N. Right. So this is lambda sitting inside an M by N box, and you can see that. So this is lambda. Let me hash it. You can see that the complement of lambda can also be viewed naturally as a partition by reversing the edges. So maybe I'll write it upside down just to give you the sense. So the complement of lambda contained in is the partition formed by the vacancies. You have to read it the other way around. So mu in this example, the figure. Okay, so another question for you is to sum lambda inside M to the M again. You can take M to the M such that lambda self-complementary. Q to the size lambda equals what? So this is an exercise. Okay, any questions about any of this? Okay, so right, so good. So now this comes us to the generalization that I'm interested in. So definition, and this, I think this figure is just in time. So you can naturally generalize partitions to 3 dimensions, and these are called plane partitions. So plane partitions you can think of this in 2 ways. So at least it's an arrangement of boxes in a room such that meaning the boxes are justified or acted on by gravity in the -1, -1, -1 direction. So for example, all plane partitions inside a 2 by 2 by 2 room are given in the figure. So they're ordered by the number of boxes. So there's the unfortunate thing of viewing plane partitions is that your brain is hardwired to interpret them in two ways. So this you should think of as an empty room rather than a full room. You can interpret it both ways, of course. So this is the floor, this is the left wall, and this is the right wall, and there are no boxes inside. This will help. There's exactly one box inside, and it can be placed in only one way. So things are forced into that corner, this corner over here. Okay, so if you have two boxes, they can be stacked one on the other. They can be two on the sticking to the right wall, two sticking to the left wall, three similarly that way, and four this way, and five this way, and so on. And the maximum is 8, and where all cells are occupied. So is this clear? I'll give you an equivalent definition. So equivalently, it is a rectangular array of non-negative integers P, which is Pij, such that Pij is greater than or equal to Pij plus 1, and Pij is greater than or equal to Pi plus 1j. Okay? So, okay, this figure I will need later. I'll push it down. So all plane partitions of 3 are, well, there is 3 itself, there is 2, 1, there's 2, 1, there's 1, 1, 1, there's 1, 1, 1, there's 1, 1, 1. So if you want to make it a rectangle, you can add a 0 here. And you can add zeros and make them arbitrarily large. So again, just like partitions, there are many conventions, and some people take the convention that it's an infinite array. I mean, one-sided infinite array with only finitely many runs of elements. Okay, so this will have to be pushed down quite a bit. Okay, so what do I do? Maybe I will cut it and paste it up. Sorry, paste it here. Okay, so I'm going slower than I thought. So okay. Yes.
Sir, one question.
Yes, please.
So, like, why can't we think of it as a sequence of partitions where the partitions on top are subsets of the lower ones, I guess?
Yes, you can. Yes, there are several different ways. Yes. So you can think of them as arrays of partitions. So exactly like Aradhya says. So you can think of this as the partition 1, 1, and this one contained inside that. Yes, absolutely. So from that point of view, So right, so that it's good that you said that. So let me give an example. So let's look at this one. So this is the first, the thing sticking to the rightmost wall is the partition 2-1. It's a diagrammatic representation. So it's the Young diagram rotated in some sense. And this is the partition 2-0. And this is the partition 2-2, and this is the partition 1. So you can think of this as sequence of partition. That's right. So that point of view will also be helpful at some point. Okay, so here are, as I said, all the partitions inside a 2x2 room. So a question. So okay. So for a plane partition, what is that? For a plane. So for a plane partition P, what is going on? Oh, it's very strange. It's very strange. I don't understand what's going on.
Maybe we just leave that line and go like write a line below.
Sorry?
Going on. We can move on, like we'll move 2 lines below. I think there's some strange thing in the line.
Maybe. Okay, let me go below. See, but it's happening again. It's very strange. Okay, let me stop sharing for a second. Let me stop recording. Okay. Oh no. Okay, let me stop sharing. I'll close it and. It's happening again. It's very strange. Is it maybe because the image was here? That's very strange. Okay, just a second. Let me open a new file and see if that works. Okay, yes, it works. Yeah. Okay, let me share this instead. Can you see this?
Yes.
Okay, so for a plane partition P, define the weight of P. So this is completely analogous to the definition of partitions. Weight of P as is Q to the size of P, where sigma ij Pij. Okay? Mod P, Q to the mod P. Okay, and now here's the question. So, can we give a form? Is there a formula for, let's say, sum over P inside A by B by C. So, oh, no, I can't. You saw the, okay, I will need that again. Okay. I'll open that again. Sorry about this. I don't know why this. I actually need this. Okay. So this was the case of A equals B equals C equals 2. Right? So in this example, okay, so now I can use Sage. Okay, so just like I did partitions in a box, I actually already have plain partition. Okay, so Sage has plain partitions, and here's a random element. Okay, let me forget about that. So what I'm asking for is I've already defined Q. So Q to the P dot size. Okay. Let me do it this way. So P comma Q raised to the P dot size for P and P. P does not have size. Okay, so let's see what P has. P dot what is P dot rank? 14. No, that makes no sense. What is that's a bit surprising. Let's see. Count. Oh yeah, the one thing I wanted to show you. So this is the partition 1, 1, 1, 1 inside 2, 2, 2, and you can see you can use pretty print for that also. So you can see there are 4 boxes. Anyway, okay, so this is done using QTaskIR. But where is size? Okay, that's strange. Okay, let me do some P. So let me, let's see if this works. So P of I for I and H. Okay, and now I can do sum of that. Okay, so that's a bit ugly, but can't be helped. Okay, so let's just check that this worked. So this has size 0, so Q to the 1, then Q squared, blah, blah, up to Q to the 8. Yeah, that's it. Okay, so now let's just sum this. So sum. So this is what it gives you. And if you factor it, something really nice happens, that it factors into very simple factors. So for example, okay. So the Q binomial, so this thing you can recognize as the Q number of 5, so which is the same as the Q binomial coefficient 5 choose 1, right? And this Q squared plus 1 is also some nice factorization. I mean, there's no obvious meaning to it right now, but it does seem to factor. So let's play around with this. So let me do 4 2 2, or let's say 3 2 2. 3 2, okay.
Sir, what is LENP here? Length P or what?
Yeah, len is length, standard command for. Okay, so now, so this is the advantage of this. I just change P and I can evaluate this function, and you can see something again nice happening. This is again factorizing really beautifully, and actually each of these factors is related to something nice. Okay, so maybe this was a coincidence again. Let me go larger. So now you see this guy squared. So and these are larger and larger factors. So something really nice is happening. And this brings me to this beautiful theorem of McMahon. This is called the box formula. So this is the theorem by Percy McMahon, 1912. This is known as the box formula. It's one of the nicest formulas in combinatorics, which is that sum P inside A by B by C, room Q to the, oh, what did I do? Oh no, I'm sorry. Sorry, I did wrote some nonsense here. This should just be weight. Or I don't actually need to. So Q to the size P is this amazing product formula. I equals 1 to A, J equals 1 to B, K equals 1 to C of I plus the Q integer for I, the Q number for I plus J plus K minus 1 divided by the Q number for I plus J plus K minus 2. There are other ways to write it which are not so symmetric, involving just two products, but this is the nicest and most symmetric. And you see there is no problem because the denominator will not be 0 because the minimum value is 3 minus 2, which is 1. Okay, so this is called the box formula. Okay, any questions about this? So, you should check that these things that we did are actually this box formula. So McMahon was quite a character. He was in the English Army, the British Army, and he was actually posted in India for about 5 years or so. And then he went back, and then he took his degree and started doing mathematics. So, and he is the one who was kind of, so he wrote this textbook called Combinatory Analysis, and that is the one that sort of put combinatorics on the map. Okay, so coming back to our theme. So just like for partitions, we had these symmetries. We had these two symmetries, which was reflection, which was this conjugation, reflection about the diagonal, and the other complementation. Here you have other symmetries. So, so if you look at the corner of a room containing a plane partition, you can see that it is a hexagon, right? So plane partition. Oh, sorry. So plane partitions can have many symmetries. So from the figure, the dihedral group D6 acts on it for A equals B equals C. So this is this case. So you can see this forms a regular hexagon, and you can you have all the symmetries of a hexagon. So this is where the two-dimensional view and the three-dimensional view are going to be messed up a little bit. So but I'll make this point clear. So so just like for partitions, we enumerated partitions without any symmetries, which was all the partitions inside an A by B box, which I called M by N box. Then we had partitions which were symmetric. Like that, we can look at all symmetries over here. So consider. So I'll try to illustrate this figure. So consider all possible symmetries, and we'll see some of these later. Symmetries that a plane partition can enjoy. So there are many of them, so let's go slowly. So first one is no symmetries. So this is the analog, this has there's no constraint there. So just to give you a picture, so we are now looking inside a hexagon. You know, this is how, so partition will be a filling of this A by B by C. So if you like, this is, well, I'm taking all A by C equal for now. One can relax this as I'll show you in a second. So when you take no symmetries, you know, there's no constraint. A, B, C can all be different. The second class is vertically symmetric. This is, for whatever historical reasons, just called symmetric. So these are partitions where these are symmetric about the vertical axis. So if you look at this figure, this is an example of a partition that's vertically symmetric. This is not, and this is not. In fact, under vertical symmetry, this transforms to this, and similarly. So this is a group of this is S2 sitting inside D6, or if you like, D2 sitting inside D6. So it's just transposition. So the subgroup S2. So we'll consider all plane partitions which respect this S2 symmetry. Then you have now we get to more complicated things. You have cyclic symmetry. So these are called cyclically symmetric. Oh, now this. So this. So here. So here this is rotation by 120 degrees. So here what this is saying is if you take this plane partition and sort of rotate it by 120 degrees, you will get another plane partition, and this will transform to that, and then that will transform to that, and then back to this. So this is this cyclic group C3 sitting inside D6. So this is a reflection in the dihedral group, and this is a rotation. But there are some which are symmetric under rotation. And the first example is the empty one. That's also cyclically. So this guy is cyclically symmetric. Let's see. None of these are. This one is cyclically symmetric. You can see. The last word also. So that is that. And then there is the totally symmetric. So which is both vertically symmetric, I should have drawn an arrow here, and cyclically symmetric. So if it is both, then it's totally symmetric, and this is under the full D6 action. So it's symmetric under the full maybe I should have written. So symmetric under, and here symmetric under. So this is the full D6 action. But so if you just look at it in this way, you only get 4 classes of objects. Oh, so I should have said, so here, for example, for vertically symmetric, you don't need all ABC to be equal. I mean, you just need 2 of them. So if you're calling this A, it can be of the form ABB. Such things, more general are allowed. For cyclical symmetric, you need all 3 equal, and therefore also for totally symmetric. But there are various conditions. Okay, so all right. So if we do this, then that's it. But remember, just like in the partition case, we have an extra symmetry which is not captured geometrically so far, which is complementation. Oh, okay, I'm switching back and forth. Sorry about that. But what I was trying to say when I was talking about partitions is that complementation is not inbuilt for the set of partitions inside a box. So that's why I could not show you. I could not say P equals P dot complement, because that function is simply not there. So this is one of the drawbacks of Sage, that not everything is already inbuilt. I mean, one has to, whatever you need, you have to build. That's both a drawback and a virtue. All right. Okay, so we have this extra symmetry, which is complementation. So it works much the same way as for partition. So for example, the complement of the empty partition is the full partition, and complement of the partition containing just one box is the one containing ABC minus 1 box, and so on. So right. So now you can ask for partitions. Okay, and it's obvious how to see for complementation. So you replace, as I said earlier, the particle hole symmetry. What physicists call. So you replace vacancies by boxes and boxes by vacancies, and turn the figure completely upside down. So then you get this complementation symmetry. So for example, the complement of this partition is actually itself, and so for this, but not for this. Actually, yeah. So if it has to be complementation symmetric, then it has to have exactly half the number of boxes, and so at least one of ABC must be even. Okay, so now let's, with this additional symmetry, now you have more possibilities. So then we have self-complementary. Okay, so now I'm not drawing the figure because it's not going to be helpful. Okay, now things get really complicated. Well, the next one is called transpose complementary. And what this means is that the complement is equal to the reflection in the xy plane. Or this transformation that takes that transforms a partition is the same as taking the complementation. And then there is symmetric self-complementary. So that is to say, it's self-complementary and vertically symmetric. Remember, I said symmetric without any adjective is any extra adjective is automatically vertically symmetric. So this is both symmetric and self-complementary. And then we have cyclically symmetric transpose complementary. So maybe all of I should have said all of these have names. So this is, so no symmetries is just all plane partitions. This is SPPs, symmetric plane partitions. This is CSPPs, and this is TSPPs. This is SCPPs, TCPPs. I think this is, we'll see them soon. Okay, so let me finish this. So cyclically symmetric transpose complementary. So now you can see what this means. This means that it's when you act by a cyclic rotation, you get the same as if you took the complement and its transpose. Okay, so it's really okay. Then cyclically symmetric self-complementary, and the mother of all of them, the ultimate fellow, totally symmetric self-complementary. So okay, so this is CSTCPPs. This is CSSCPPs. I think this is SSC. And the ultimate TSSCPPs. So why did I bring up all of this? So okay, so before I do that, let me show you. Crashed. Okay, so just a second. Let me stop sharing for a moment. Any questions meanwhile?
I mean, do all of this turn up naturally or show up naturally, or like 10 to?
Yes, that's a good question. So I was going to write that. So amazingly, just like the box formula of McMahon, all of these have product formulas, with no exception. All of these have beautiful product formulas, and we will see some of them. So, okay, so let me. Okay, let me share again. So these are the 7 TSS CPPs. So all of these enumerations have nice product properties. And it is still an open question why that is the case. I mean, the methods for all of them are very different. So in particular, one of the biggest open questions for a long time was cyclically symmetric plane partitions. Their enumeration required lot more. So that was an open conjecture of MacDonald that was proved by Andrews. So so the techniques for all of them seem, although related, not completely the same. You have, so it's not, a global picture is still kind of missing. Okay, so as I said, so for size 2, this fellow is the only TSS CPP. It has all the symmetries of the square, of the hexagon, and also complementation. So totally symmetric plane partition also satisfies all these other symmetries, right? So that's the thing. And okay, so here is the point of introducing all these fellows. So theorem. So originally conjectured by Robbins and proved by George Andrews in 1994. So TSS CPPs only exist for 2n by 2n by 2n rooms. So not only should A equal to B equal to C, they should be even. So the number of TSS CPPs in a 2n by 2n by 2n by 2n room is equal to, again, the same. This is the same as the number of ASMs of size. Okay, so this is, for example, the 7 TSS CPPs of orders, let's say in a 6 by 6 by 6. Okay, so this is from Rasool's book. So this one is kind of obvious. This is the thickening of this guy over here. But the others are not so simple. You see, they have quite a bit of structure, and so it's not completely clear why this has to be the case, right? Okay, so any questions about this? So now we have 3 classes of objects which have the same enumeration, and let me spend a little more time explaining how ASMs came up in another context. Should keep saving. Okay, so right. So this is called the square ice model. So this is a model in statistical physics. In Z2 in 2 dimensions. So this is this is one of those what are called exactly solvable models. So I'll not get into it. Let me just give you a figure to illustrate the point. So so recall that water molecules H2O has the property of hydrogen bonding as an extra bonds. Well, bond not really, hydrogen bonds. So these are, you must have studied this in chemistry. So what this means is that the oxygen is strongly attached to 2 hydrogens, but it's also weakly attached to the hydrogens of the other oxygen. To the other water molecules, to the hydrogens of the other water molecules. So let me show you the figure of this model. So I'll go back here. So this is the figure I wanted to show you. This square is. So I'll paint it here. Okay. So what we do. So let me just illustrate. So we'll have a square grid. So our model is the following. So oxygen atoms on the vertices of a square grid of Z2. So like so, here, like that. And hydrogen atoms halfway between the edges. Joining 2 oxygen atoms. So both vertically and horizontally. So the vertices are really at the oxygen. Okay, so these are not hydrogens don't sit on the vertices. Okay, each hydrogen is attached to one of its 2 neighboring oxygens, as in the figure. So this hydrogen is joined to this, this hydrogen is joined to this rather than this, and weakly linked to the other. So if you want, we can actually draw dotted lines like that. Okay, so they are also linked. So that's why the hydrogen bonding is necessary. Otherwise, you know, why would they stay in a grid? Okay. So is that clear? Now we will impose the So the original square ice model was on all of Z2, but we'll look at a finite version. So consider pose on an n by n grid such that the hydrogens such that okay, so the ones on the left and right boundary. Oh damn, I forgot to say. So oh shoot. Okay, so as I said, I will be having an assignment in the last 10 minutes. So I've already assigned it actually in Microsoft Teams. So to take, so those of you who are not interested in taking the assignment, you can leave when I tell you to. But those of you who are, I've given you a programming task to do. And it will, so what you should do is log into CoCalc, create your file with your own name as I asked you to if you have not already, and write the program. So the instructions are there, the name of the program is there in the assignment. Write the program and submit it as an answer in the quiz when you are done. Submit the entire program block and leave your CoCalc file with your name with that program so that I can test it. Okay, so it is time constrained and I'm just experimenting. So I've given 10 marks for this, and I just want to see if such a thing works. Okay, so I'm going to start. It will start exactly at 12:50 and it will end exactly at 1. Okay, so I will, so please look at the assignments tab and when I tell you to, and please keep your CoCalc open and ready with your, just open your file, don't open any other's file, just open your file and look at the assignment and program it. It's an easy assignment, but yes, so I'll see how it goes. I would like to grade it, so please do it seriously. Okay, maybe I will do it. I will grade it in any case, and maybe I'll drop the lowest grade at the end, as I usually do. So please take it seriously, and because I want to see if this kind of grading is feasible for the future. Okay. Are there any questions about this quiz? So I'm also creating the quiz the first time, so the instructions for creating the quiz are a bit complicated in Teams, so I might have messed up in the creation also. So, but in any case, I will give you extra time if you need it or whatever. I mean, I'm willing to play around with the parameters, but I want to see if such a thing is feasible. So please take it seriously, okay? And the programming assignment is itself not hard, so it should not take you 10 minutes. So I've given you, I think, enough time to do it. Okay. Okay, so let me finish this statement. Okay, sorry, I get distracted all the time. So, okay, so now what the boundary condition is that the oxygens on the left and right boundary are attached to H's outside. So in this example, this is a 1, 2, 3, 4, 5 by 5 grid. So figure is 5 by 5 grid. So So these oxygens on the left boundary are necessarily attached to the hydrogens outside, left and right boundary, and the ones on the top and bottom boundary are not attached. To the ones outside. So exactly as the figure. So let me have that. So these ones are attached and these ones are not attached. Okay, this is forced. Okay, just like this figure. So this oxygen none of these oxygens can attach to the hydrogen above and none of these can attach to the hydrogens below, but on the left and the right they do attach. Okay, is that clear? So let me give you the example for n equals 2. Again, I'm horrible at drawing, but I'll use the line and get. I can't draw arrows yet. Okay, so for n equals 2, I have these, right? And okay. Okay. So sorry. Okay, so let me tell you. So this is the system. Okay. So what we are interested in doing right now is just counting how many such configurations are there. So by configurations we will mean attachment of the H's in between the O's to the O's, which satisfy the condition. Okay, so each hydrogen. Okay, here I should have added, of course. Oh, shit. Of course, each O should be attached. It's hydrogen, it's a water after all, to exactly 2 H's. Right? So it's of course water, so I cannot have 3 connections to it, or 3 or 4 connections. Okay? So every oxygen is connected to 2 hydrogens, like in this example. Okay? Okay? Whew. Okay, so what is an equivalent way of looking at this? I still have 10 minutes. Okay, so I should be able to finish. Equivalently, represent each O by a vertex and denote or rather determine the bond of H by an arrow. Okay, so if between these two O's the H is connected here, like in this example, I will draw an arrow from bottom to top. And here, like in this case, I'll draw an arrow from left to right. And here I will draw an arrow from top to bottom, like that. Okay, so that contains all the information, and I will add half edges on the boundary, pointing inwards horizontally, that corresponds to these guys being connected, and outwards vertically. That is to say these guys on the top and bottom are not connected. And the last condition, which is because it's water, is that every vertex will have two incoming and two outgoing. So let me give you this example. Okay, so let's do this quickly. So as I said, oh damn, I could have done this. So these are all pointing inwards and these are all going to point outwards. And now I have to assign arrows to these four edges such that this condition is satisfied. Oh, sorry. This is inwards, and this is outwards. So this condition is called the ice rule. Last one. Okay, so let's see. We will see that pretty much fixing one will fix all the others. So suppose I choose this one to be pointing leftwards. Then you see I have, for this fellow, I have two outward pointing edges. So the next one has to point inwards. Now let's look at this one. There are two outward pointing edges, so the next one has to point inwards. Now let's look at this one. So there are two outward pointing edges, so the next one has to point inwards. Similarly, so you can see that this guy actually, these 4 points go counterclockwise. You will see by similar argument that this will go counterclockwise. Okay. Okay. So and again, you see the number is 2 for size 2, and you can guess what's going to happen. So actually, it's an easy proposition. The number of, oh, okay, I should have said, this boundary condition is called the domain wall boundary in the literature. Okay, so I'm running out of time. Okay, so the proposition is that the number of square ice configurations on n by n grid with domain wall boundary conditions is equal to an again. This is easy to prove, no, not trivial, but easy. And to see this, so to prove this, I have to look at the local configuration. So how many local configurations are there? So let me draw it. So let's see how many local configurations are there. So this can point right, these two can point up, this can point right, these two can point down, this can point left, these two can point up, point left, these two can point down. Or so here the arrows propagate through the vertex, but then there are two special cases where they do not. Both inward horizontally and and outward vertically, or the other way around. So inward vertically and outward horizontally. Okay, and the idea of the proof is that this one, so given, so there are 6 of them, that's why these are also called 6-vertex. This is also called the 6-vertex model, or square ice model, 6-vertex model. So the proof idea is that so given square ice configuration, replace this guy by a 1, this guy by a -1, and rest by zeros. So this shows you how to get a configuration. So as an exercise, I would suggest that you try to find the alternating sign. So you will get an ASN this way bijectively. So I recommend that you try this over here for this figure. And this is not completely obvious because this tells you how to go from 6-vertex model configuration to an ASM, but how do you go the other way around? That's not completely obvious. So again, I will ask you to fill in the gaps. So exercise, fill in the gaps. Okay, I think this is a good time to stop.